And perhaps give it another minute and then we'll make a start, as we've got most people. There's a few that haven't turned up yet, but yes, I've just got to warn up to you that we are now recording, so just to let you know that we're being recorded. Right, I'm going to make a start, I think, and then I'll keep an eye if anybody else comes into the lobby. Well, as it says, I'm Simon Green from Green Build Design, and we thought we would do a lecture. You know, we've done ones in the past on energy efficiency and really what does it mean. But obviously, with this massive rise in fuel costs and everybody talking about energy, we thought we would give some general advice on what does going green mean. Is now the ideal time to do it? Anything you're thinking of doing that saves energy clearly will have half the payback at current rates, and also some ideas on how you could potentially save energy and obviously save some money going forward, as clearly it's going to be needed for going forward. I'm trying to do two things. I'm trying to watch the lobby and I'm trying to move on to the next slide, which I can't seem to do. Good day for IT problems, is it? Right, off we go. So when you obviously talk about green energy, everybody would normally disassociate that really with wind, wave, tidal, or obviously solar energy, converting those sources into electrical energy. But really, anything that's going to save you energy, we would consider a green technology. Broadly speaking, those technologies that are going to save energy, plus provide some similar results of using, you know, any fossil fuel. Significantly, energy savings obviously can be made by improving the thermal U values of the walls, of the windows, and the roofs. And obviously, that is something that everybody will be focusing on new build houses by improving those U values. Now, one thing is, it might seem an obvious statement to say in the UK, but even with our mild summers, still extreme care is needed on lots of new build houses. They're heavily insulated, heavily sealed, and there's a real strong chance that they then overheat in the summer. So it's always very careful to ensure that you've got very good cross ventilation, which probably needs to be done via modelling. And you know, assuming that if you've designed that house to have the windows open for summer cooling all year round and during the night, you know, is that actually achievable with noise pollution or even the noise or traffic pollution? And you know, obviously, if you have got to cool that building during the night, you know, from a security point of view, is it actually safe to have the windows open all night? So you know, really, with insulation being the biggest thing to do on certainly new build, it's just been that real careful loss about not over insulating your building. And then really the more common things, and what we're going to spend most time talking about, is obviously more energy efficient plant, which, following the government guidelines, is really going to be the use of a heat pump. So what are heat pumps? Those are some heat pumps examples. They're basically an electrically driven machine that is able to heat or cool our buildings and also provide hot water. And they're called green machines or low energy machines is because by using electricity, they can extract more heat than you input. I'm going to talk about this in more details. And as the government plans to get our national grid much greener and use less fossil fuels, the idea is to get national grid completely green on renewable energy, and then have everybody using electric cars and electrically using heat pumps, and therefore the country by default will be carbon neutral because we're not using any fossil fuels. So that's why really governments are pushing the use of air source heat pumps. The sorry, I'm having a bit of a problem with the slides here today. I don't know what's going on. I seem to Right, here we are. Sorry about that. So the way a heat pump works using refrigerant technology is that, depending on the models and the conditions, you can typically get 3 or 4 kilowatts worth of heat into your building to either provide heating or hot water, and dominantly use 1 kilowatt of electrical energy. So you could kind of say that's a bit like magic, really, isn't it? 1 kilowatt in and 3 or 4 kilowatts of heat to your space. Obviously, if you compare that to a gas boiler that's running at 95 or even 97% efficiently, that means you've got to put 103 in to get one back out. So that's really where the efficiencies lie in the technology of the machines. Now, the terms of their level of efficiency is often referred to as a COP. Now, that is a definition as a coefficient of performance. And that really is the manufacturers giving you, during an exact set of conditions, an exact external temperature and an exact internal temperature, how efficient the machine can produce that. And you'll typically see that as a number anywhere between 2.5 and about 6 on a specific set of conditions, which obviously isn't that helpful when you're trying to select a machine, because every day the different temperature, during the day there's different temperatures, you may want different temperatures internally. So what the manufacturers try to do is they try to take an average over the whole year, and they call that the SCOP, the seasonal coefficient of performance. So when you're looking at these machines, it's really, really important. A bit like when you look to buy a house and have your EPC certificate there. If it's got an A rating, you know it's going to be using less energy than if it's got a G. And consequently, when you choose one of these many air source heat pumps, you need to be trying to get one with the higher number of SOCP, which is how efficient it's going to work. Now, basically, to keep these efficiencies high, we need to design it properly, and it needs to be managed and run properly. So, as well as air source heat pumps, there are many other things that we can start looking at. Obviously, solar panels can go on the roofs. There's a picture there showing some solar panels. And you can also, the picture slightly at the front, it's also showing water panels, which is able to directly heat hot water. Obviously, insulation and thermal insulation going on, we've talked about. Controls is one of the biggest ones that we could look to do. And obviously changing all of our lights to LED lamps. LED lamps use a fraction of the energy of GLS tungsten lamps. Can be down as low as 10%, and probably about 30% of fluorescent lamps. Controls that automatically switch off the heating, lighting, and other services. Obviously, insulation we talked about is clearly going to save energy. Now, obviously, when we talk about green energy, we tend to think this is a new development and has not been around for very long. But there's a couple of slides there. Look, one in the middle of 1902 was a primitive solar water heating system, which comprised of a cast iron tank and a wooden box, which obviously gave you a free tank of hot water each day, obviously demonstrating that this has been around for over a century. And in fact, the first solar powered station was built in Egypt by the British in 1912, and that was providing electricity to pump water from the Nile into local cotton fields. So challenges with green. This is always the problem. Probably the most one of the most biggest challenges we have is the upfront costs. Going green is going to cost you more than staying with your boiler. Now the costs for being, sorry, beg your pardon, the costs for using green technology, if it's properly designed and properly laid out, will provide paybacks. Now, some of those systems can give you a payback in 18 months, and some of them can extend towards 20 years. But I will tell you now, the one thing that doesn't really pay back is an air source heat pump compared to gas boilers. Now, you can buy various grants from the government, and you can look at those, and those will obviously assist and help on those paybacks. But if you have a salesman telling you that he can put an air source heat pump in, take the gas boiler out, and he can pay back in a couple of years, he's probably stretching the truth a little bit. And basically, air source heat pumps are going to be the preferred choice of the government. There will be some grants around for it. And, the days of having cheap gas heating, I'm afraid for most of us, are unfortunately going to be, disappearing, be a memory of how it didn't used to cost much to heat our houses, and now it does cost more, and it costs more to put that equipment in. And that's the realities. The other constraints we need to think about with air source heat pumps is the size of the plant. We need a large unit outside, and we also need a unit inside, and potentially we need some air handling plant to control the amount of fresh air coming in. So the space that the plant needs is much more than we've been used to. And probably most importantly is if you have a combi boiler at home, combi boiler works on, it provides constant hot water by instantly burning a lot of gas and simultaneously heating up hot water. Compared to all air source heat pumps, which need a hot water cylinder. So again, there's another space needed then for a cylinder to be placed somewhere. They tend to need more maintenance, and they need to be commissioned properly. And externally, they need to be in a good space, which can allow a lot of air to come in and around them. And to get them to work better and more efficiently, it's really important that they go in the south and west facades, where typically you have a garden or more of a view. And often people don't want them put there, they want them put around the north or east facades, where they don't get any benefit of solar radiation from the sun. But again, I'm trying to tell you how to be more efficient and save more money. Retrofitting these into existing houses does have some challenges, mainly because boilers work at higher temperatures than the air source heat pumps. That does become a challenge to need to be properly designed. The biggest challenge is when you have a air source heat pump, I think, or a ground source heat pump, is when people talk about the costs. Now, we have already talked about the SCOP, which is your seasonal coefficient of performance for heating. There is another term that gets used, and that's the SEER. I don't know why it's codes, we keep having all these names, but engineers are good at that. And that stands for the seasonal energy efficiency ratio. And that's the term it's used for cooling. So if you're going to cool your house, you'd need to look for your COP or SCOP for winter, and then you look for your SEER for how it can then cool your house or cool your office in the winter. Sorry, in the summer. Now, let's take the cost of electrical energy. It's very topical at the moment. Compare that to the cost of gas. Now, with them constantly changing and fluctuating, it's all difficult, and you have to take a line in the sand of a date and look at that number. But typically, it's about 2.5 to 3 times more expensive for electrical energy compared to gas. So what that really means is you must select a machine that has at least a COP of 3 to 1, basically, because if it doesn't, then it could be costing you more to run than a gas boiler. And all the times it's running above that COP, it's saving you money towards the capital cost. So if we take an average machine with a COP of 3.9, again, that means for every 1 kilowatt of electrical energy in, you're going to get 3.9 kilowatts of heating or cooling into your space. Then if you compare that and think about how a typical air source heat pump would have an SEER, that's the cooling ability, of between sometimes 7 and 10 to 1. So again, that's amazing. 1 kilowatt of electrical energy in, and you're getting 10 kilowatts of cooling to your space. So back to heating. The COP, so that is the specific temperature outside against the specific installed temperature. To give you some idea of manufacturers, when they are coming into cold weather outside, they're obviously not quite sufficient. I guess that makes perfectly good sense, isn't it? When it's really cold outside and you're trying to extract latent heat from the air, it's more difficult than if it's at 25 degrees. So manufacturers Mitsubishi EONAM units quote that at -7 outside, the COP is about 3 to 1. So depending on exactly what you would have been paying for gas and electricity, that's on the cost, but actually might at that specific moment cost you more to run than a gas boiler. At -3, it jumps up to 3.4. At +1, it's about 3.9. And at about 25, so if you think in the summer when you've only got hot water leads, manufacturers seem to be suggesting it's about 5. So if you use a lot of hot water and use it a lot in the summer, then you are going to save a lot of money compared to your gas boiler. Help start to repay that extra cost. And basically these graphs here are trying to show, the middle graph there is just really trying to show how, to have 100 kilowatts of 100 kilowatt hours of heating, your gas boiler is going to cost you, just over 100 kilowatts of that, compared to sort of 30 kilowatts with your air source heat pump. And obviously energy is charged on kilowatt hours, so you have 30 kilowatts of electrical energy against the 107 kilowatts of gas energy. So you can see you use a lot more energy. The problem is it's just slightly cheaper. So if I take Greenville Design's offices as of the 1st of April, we are unfortunately having to pay 28.4p for a kilowatt hour of electricity against 8.8p for a kilowatt hour of gas. So this second graph now on the right hand side is now showing how that can work on costs. Now, running through the maths, if we assume that the COP of the machine was 3.1 in the winter, and therefore again you're getting, for every kilowatt of electrical energy in, you're getting 3.1 kilowatts to your space, so you're getting good efficiencies. Times that then by 100 kilowatt hours, that's coming out at £9.46. Then if you compare that to a typical gas boiler with a 94% efficiency, it's coming out at £9.36. So that's actually 10p cheaper to run those 100 kilowatts in that condition of internal temperature against external temperature, which clearly is quite a shock to some people, including engineers, who just had to know. Now, having highlighted that maybe the air source heat pump isn't as grand and grandiose as I'm saying it is, I mean, clearly it's going to save an awful lot of carbon. It's going to save at least a third of carbon, and it may be down to 20% in the summer. So from that point of view, from carbon, there is great savings. What can we do to make the air source heat pump work better? So in a domestic house, we've got to look at the thermal insulation. And if it's a new house, then clearly it can be built very well. And if it's an existing house, we can look to add insulation internally, change the windows to double glazed, stop air infiltration leaking in through drafty doors and windows, and add insulation obviously to the roof. We could also look at your hot water demand. Now, hot water on air source heat pumps takes a while to heat up. It uses air source, it uses latent heat, and it will need to typically charge into a hot water tank. So it needs to be really careful how we size that tank, because what we really need to ensure that in the afternoon the hot water is charged up using the air source heat pump, hopefully in the south or west facades where you're getting from solar radiation and the warmest weather. And then that tank then uses your water load all day. So we really need to start very carefully matching and make sure you're putting in low water use showers, typically you'd get in a Premier Inn, which gives you a nice hot pressurized shower. And things like rainwater showers, which are very pleasant and nice, you have to understand they use an awful lot of hot water. Now, if the system hasn't been designed for that, then the chances are you're going to drain that tank of hot water down. And if you drain that hot water tank down, you have a choice. You have no hot water and wait till tomorrow, or you ask the heat pump to heat it up, which will take anywhere between 2 to 6 hours, depending on settings and the temperatures. Or, as some people do, they put the emergency only use electrical immersion heaters on. Now, at that point, you have electricity running at 1-to-1, charging up your tanks back to hot water. So it can be done, and it does work relatively quickly. But of course, you're getting no carbon efficiencies, and you're paying, 28p a kilowatt hour for those immersions to run for every minute they're on, compared to 8p for gas, and obviously not getting your efficiencies on the air source heat pump. So I do have some people that have got air source heat pumps in, and they say their gas bills, I beg your pardon, their electric bills are massively more than their than the gas bills. And when I go and look and interrogate, I find they have the immersion switched on because nobody's ever told them to switch the immersion off. Or they said they keep running out of hot water, so they leave them on to ensure they have hot water because the things haven't been designed properly. So again, it's absolutely critical we get the hot water tank sized correctly. And if you change the showers or the taps from one type to another, you should talk to an engineer to make sure they're having similar flow rates, or you will have problems with maintaining hot water and costing you a lot of money. The other main efficiency thing is a gas boiler typically works on providing hot water at between 70 and 80 degrees out of it. Now, at that higher temperature, it's very inefficient for an air source heat pump to produce that higher levels of heat. So typically they want to be between 45 and 55 out. Now, if you're retrofitting a boiler into your house with radiators, we need some careful thought on the size of the radiators, because if they're used to having 80-degree water and then you drop that to 55, it means that not the same quantity of heat comes out. So there is a possibility that either the radiators would need to be supplemented with additional ones or replaced, or it could be that you're lucky that the thing was so over designed in the first place that when you've done a model and the calculation again, it is actually large enough. But that's a big problem, is to make them run efficiently, we need to run at lower temperatures. Now, air source heat pumps work very, very well with things that use lower temperatures, like underfloor heating. So again, if you've got a new house, underfloor heating is probably what's going to get installed, and that works very, very well at lower temperatures, usually at 45 degrees. Again, helps with heat pump efficiencies. And again, that needs to be on for longer periods of time to allow the heat from the floor get into the space and warm it up. So to give you some ideas about these efficiencies, and we've got a couple of examples here. So if you take my example one, which is a new house. Now at this stage, I'm only looking at the heating. I'm not going to consider the hot water. And the new house is going to have underfloor heating with a 45-degree flow temperature and a 35-degree return temperature. It has got a hot water tank, which is a large tank, which is going to be stored at 50 degrees. And then there's a weekly immersion comes on just to top it up to 60 degrees for an hour, just to kill off any potential Legionella in your hot water. Now, the manufacturers are saying that that particular unit we were looking at for this job had a seasonal coefficient, so that's the average for the year, of 4.88 to 5.1. So if you think back to your electricity energy is sort of 2.5, 3 times the cost, clearly with that example, you are going to save quite a lot of money compared to a gas boiler, provided it's set properly and commissioned properly. Now, if I compare that then to an existing house that had gas-fired boiler heaters, the output temperature was 80 degrees and the return was 60, so using a lot of energy across those radiators, when hot water was stored at 65. So my problem now is I'm worried that storing water at lower temperature means I've got less hot water in effect to serve those showers. So there's a risk now that that tank isn't large enough to suit your needs. So that's something we need to look at. And then obviously with the radiators, there's a risk that we may need to replace some, or we need to add some with that lower temperature. Now there is a manufacturer on the market, a Daikin Altamira 3 HT, that also has some electrical element heaters in there, which are able to push the water up to 70 degrees. So you could potentially sacrifice doing work in the house with the hot water cylinder, with changing the radiators or adding radiators, by adding this new unit in that in effect has some immersion heaters that top it up. And that same machine then, it drops down from sort of 4.95-ish, and that will drop down to 3.5. So you kind of get to see how the efficiencies drop because you're putting immersion heaters on to bring that temperature up. And from a carbon point of view, you're still probably using a lot less carbon than your gas boilers, but in terms of cost, you're not probably saving a great deal of cost money. But there's a lot of options to what you can do, and you just have to stress that before you go down this ride of getting air source heat pumps, you do need to get some professional advice from the manufacturers, from engineers, and at the moment, some contractors don't know enough about it, and they need a few more years to learn about the pitfalls with it. But if you're retrofitting in your house, I would definitely recommend you get some consultants' advice. So I wanted just to bring this slide in as it's much more topical than to think about, not knowing exactly who's on the audience and who's there, but just think about the costs. I'm asked all the time, yeah, okay, I haven't got 15 grand to put an air source heat pump in, but what can I do to save energy? And then when you have a chat to people, they do silly things. And, in my house, I'm constantly having a row with my wife, because if we have a cup of tea, she'll fill the kettle up to the top, heat the whole kettle of water up, pour out 1 or 2 cups, couple of hours later, get another cup of tea and fill it up again. Now, it's difficult to know there's as many millions of kettles on the market, but looking at the kettle in our office and measuring the time it takes it to take tap water up to boil them, we've estimated that costs 10p at current rates in our office at 28.4p a kilowatt hour. Now, that may not sound like much to you, But how many cups of tea a day do you have at home when you're working at home now? 10 pound a day times 365. So that could be, you could easily be spending £300 to £400 a year on boiling kettles of water for cups of tea. Now, if that was 25% full for your 2 cups of hot water, it drops down to 25% of the costs. So potentially, by only filling the kettle proportionally to what you want, you could look to save £250 a year in that scenario. Frozen food is another good one. How many people cook with frozen food? Frozen food adds 20 to 30% of your cooking times. So if you let it de-thaw naturally and then put it in, and I appreciate it says cook from frozen for best results, but I think that's more about the safety and ensuring that it's not going in the fridge for ages. But there are options there, if to or reduce your cooking from frozen, either by de-thawing or buying products that aren't frozen. Now, ovens vary enormously between costs, and we've looked at a few ovens, and we think, on average, the cost of an oven is between £1 and £1.70 per hour to run. Now that depends on if it's fan assisted, if it's convective, what temperature the door are. But if you don't think it leaves as much energy, touch the door. The doors are all hot. You keep opening the door to check what you're cooking. That lets the hot air out. And again, how much cooking a day do you do? But ovens, electric ovens are expensive to use, and clearly, if you can avoid frozen food, that will help. Hot water use. I've talked about hot water use, and to give you a few examples of what things cost. If you have an instantaneous electrical shower on the wall, which ironically I see people are starting to go back to, with the options of not using gas or having an air source heat pump, but haven't got the space for a hot water tank, or can only have a small tank that will just do the taps. Instantaneous showers are coming back in where they perhaps weren't so popular 5 years ago. So taking a typical 12 kilowatt instantaneous heater, which is what they are, a 10-minute shower costs you 56p. I don't know if people realise that or not. I think that's a lot of money. Now if you had an old-fashioned electrical immersion and a tank, and you end up using the whole tank on a deep bath, as my wife always does, with a 4 kilowatt immersion heater on, typically hour and a half to heat up, then the costs of that are about £1.14. So £1.14 for a bath. Now, if you compare then that shower to a gas, if you compare the bath to being heated with gas, that probably drops down to about 53p. And if that gas heater heated the shower, or the air source heat pump heats the shower, you're probably at about a third of that. So it's probably about 20p for a shower. But again, if you're looking at 20p for an air source heat pump for a gas shower against 60p for a bath, it starts showing that baths are quite expensive and they use a lot more water. And going forward, I really think governments are going to start insisting that houses are limited maybe to one bathroom or one bath, or even have no baths. And there's certainly a lot of push at the moment to try and get people in new houses not to have baths but have showers, because they use so much less water and therefore so much less energy. So if you're looking at saving money, I would kind of probably say is cut the baths and have showers. The next big thing I would like to say I think you can save money on is LED lighting. Every lamp in your house, when it fails now, you should be changing it not to a GLS lamp, not to a fluorescent, but to an LED equivalent. They use between 10 and a third of the energy, depending whether fluorescent or GLS, and they tend to last longer. Some versions can be dim, some not, but LED lighting is definitely going to save you a lot of money. And if you're like my house and you've got kids, and every time you walk around, you go to every room and switch the lights off, educate your children to switch the lights off when they're not in there, reward them or fine them. I think personally, PIR's presence detectors that switch off the lights when nobody's in the rooms are a bit over the top in domestic houses, but they're certainly not in offices. And that makes tremendous savings to have daylight dimming and have PIRs that switch lights off in offices, and certainly something that will be saving you a lot of energy. I think the next thing to think about then is tumble dryers. I mean, we're getting slightly better weather now, and it always irritates me in the depths of summer when my wife puts our tumble dryer on. Now again, tumble dryers come in all shapes and sizes and different power factors. You can look at the EPCs on them and you read those and you probably won't buy any because none of them are great because they use electrical element heating, one-to-one efficiency. So there's no air source heat pump efficiencies and electrical energy is expensive. A typical cycle with clothes, not towels, uses about 4.5 kilowatt hours to run on a typical cycle, which equates to £1.29 at our prices in this office. I don't know if that surprises people or not, but every time you put a tumble dryer and it's £1.30 and it goes on 3 times a week, it goes on about 6 times in our house, you know, it starts showing how much things cost in your house. Now, assuming again you were doing 1 cycle per week, you know, that's £66 a week. You can double it up yourself, and maybe there's an opportunity where we should start thinking about using the tumble dryer less. Environmentally great and in your pocket, fantastic. And then the final thing I wanted to think about is we've recently just done a brand new house. It's quite a large house. It's 4 bedrooms. It's got 3 bathrooms, and this is having air source heat pump in. But as we had all the modelling done, what we did is we changed it from an air source heat pump to a gas boiler. Now, just the heating, because we've excluded the hot water locks from this, running our thermal model over a year, this new quite large modern house, to heat the whole house to 21 degrees was going to cost just under £2,500 a year to heat. Say that's at April's prices of 8.8 pence a kilowatt hour. Now we've kept everything else the same, and all we've done is we've dropped the set point from 21 to 20, and that dropped the cost down to 1,950. So again, there's a saving there of £550. Went down again to 19 degrees. That went down to £1,500. So if you could then lower your thermostats and your temperature in each room from 21 to 19, that will save you £1,000 a year. I think a lot of people would be more interested in that. Again, to follow the same, if you go down to 18 degrees, it goes down to 1,050. 17's getting a bit chilly now, I'll be honest, down to £800 a cost. And if you went down to 16 degrees, it would go down to £550. Now, I'm not suggesting we all go down to 16, but it does show the difference it makes, you know, and maybe what we all got to do is turn the thermostat down and buy each other jumpers and slippers, which I know is something I've said in the past before, but it does reiterate the point on real money there that, you know, there is £1,000 to be saved there by knocking your house down by 2 degrees on the set point. So PV, in my opinion, every house in this country should have PV on it if you've got a south or west facing roof that is not shaded by trees or other buildings. What we've done here is we've done a little model of an office block, and this office block is going to be air conditioned. So the benefit of this model is obviously the air conditioning runs typically in the afternoon when it's hottest, and obviously your PV will be working at its maximum input load from the sun in those south and west facades where the sun is in that area. So all of the PV you're generating typically is then going to serve your air source heat pumps or your cooling systems. So you're getting the full value of the charge out rates, and you're not exporting to the grid, which doesn't obviously make a great deal of money. And really what you can see is the cost to provide cooling to that building during the summer is basically 4,452 kilowatt hours compared to 3,500 kilowatt hours with the PV. So the PV is dealing with you know, nearly 25% of that cooling load for an office building. And again, the size of that roof compared to that building. Then if you have PV on your roof at home in your house with your air source heat pump, absolutely essential. You try to put the air source heat pump in the south and the west facades, and the controls is absolutely set by the plumber who will tell you that you know what you're talking about, and he's been doing it for years with a gas boiler and setting it to the night time. And I see many houses where the air source heat pump time clock brings the hot water on at 3 o'clock in the morning. At 3 o'clock in the morning, there isn't much sun around, so your PV is not working, and the air temperature is probably the coldest. Your air temperature is the hottest in the afternoon, and if you have your air source heat pump in that southwest facade, it will also be picking up any solar energy that's around and radiation. Therefore, you can try to get your air source heat pump, one, running efficiently, and two, using the PV almost free of charge. And that should be what we're trying to do as a goal. And if you can do that, you will start seeing some fairly major savings on running your air source heat pump compared to other people that don't experience the same. So the future, the current plan for this country is that electrical energy was considered quite a polluting or high carbon emission type product to use. Therefore, it carries embedded and hidden carbon taxes. So the government paid carbon taxes to use electricity, and at the same token, it encourages us to use it. So I think as the electrical grid becomes greener, there's going to be a lot of pressure on the government to remove that tariff from electrical energy, which it encourages us to use, and put it on oil and put it on gas. And I see a fairly soon where electrical energy will suddenly become cheaper at the same time that gas energy starts to really come up. And that will obviously help on all of the variants, help on the efficiencies, and will make air source heat pumps more attractive. Government has got to disencourage us to use gas, because gas is just too cheap and too easy. And therefore, I can only see that happening with lots of sticks and carbon taxes. Air source heat pumps are continually being improved and derived, and I think their efficiencies will drive up, which will obviously make it cheaper to use. You need to also remember that from 2025, no new buildings will be allowed to have gas-fired boilers in them anyway. So we are going to have to get used to this way of working. Government are keen to try and encourage us all to take our gas boilers out and put air source heat pumps in. So there are all sorts of grants around. So I think it's worthwhile people trying to, find out what grants are around and obviously take advantage of those. But in summary, really, my generation, I'm not quite sure the age of everybody on this call is, we've been too used to having cheap gas and relatively heating our houses for very little cost, and having a limitless hot water again for very little cost. And going forward, that time is going to change. With the horrible war that's going on at the moment, that is actually changing much quicker. And it's now bringing it to the future that I feel our only solution now is to all try and look at using less energy and cutting down as we suggested, and ultimately changing over to air source heat pumps. And with that, I'll put over to the questions. So if you've got any questions, come off of mute and I'll do my best to answer them. Come on, don't be shy. No questions at all?
I have one.
Oh, okay. Oh, yes, no problem.
If you're considering a lot of the building stock in the UK is Victorian builds and it's quite difficult to insulate, how do you see that efficiency working with air source heat pumps if you can install them?
Yeah. What we would typically look to do first, Holly, is get a 3D thermal model done of that building, and then get 12 months of our last bills, and then change the criteria of that model so that it carefully reflects the bills and the energy use, so that we've now feel we've got a model that's fairly accurate. And then we can typically run about 15 different elemental changes. So we can put some insulation on the walls to see the impact. We can change the windows, see the impact. Put some insulation on the roof, see the impact. Change the light into LED with PIR controls and daylight sensing. Go through, change the heat system to air source heat pumps. Look at sealing the building up. So there's about 15 different things we can look at, and then you get the impact on the EPC and the energy saving for each of those things. And then we can run probably about 6 or 7 models with multiples of them. And with that, you can then really drill down and see how's best to spend your money on what improvements to get. And the way the government software is at the moment, unfortunately, you don't get much credit for insulating walls, windows, and roofs. you get all of the energy savings for coming away from a gas boiler to an air source heat pump with better controls and changing to LED automatic lighting. And that has the biggest impact on energy use. It's quite scary how much energy lights use and poorly controlled heat systems. And then also, full fresh air systems that don't have any recirculation. So that those would be how to go forward. But I mean, it's a massive challenge because there's all sorts of buildings that don't have roof space. Potentially the power needs to be upgraded, and I guess we've got to take each building on its own merit. Sorry, John, did I see a question there about what's the difference between air source and ground source heat pumps? Just trying to work out how to get to the inbox. I've got so many screens open here. Basically, a ground source heat pump works very much like an air source heat pump, but the heat exchangers, instead of being in air and pushing air across them, are buried in the ground, either a 200-meter deep borehole, which goes down through the ground and warms up, or what's called a slinky coil, which would be 1.5 meters down in the ground, typically 1.5 meters across, and that goes around your garden. And then there's a gap of 1.5 meters of ground to stop your ground freezing, and it goes around. And we've only ever put one ground source heat pump in because we get to the feasibility stage and somebody says, gosh, how much is it to do the boreholes? Typically it's about £5,000 or £6,000 to do a 200 mil deep borehole, and you typically get about 5 kilowatts of energy out of them. So if you took a typical house of say 30 kilowatts, modern days now, you need 6 boreholes. That's 30 grand to do the drilling. Then you've got to get all the pipework in it. Then you've got to deliver concrete. Then you've got to get that back to the unit, compared to perhaps a sorry, John, do you come off mute, John, because I can't seem how to get my inbox up, so I can see your questions come in.
Sorry, can you hear me, Tom?
Yeah, no, hear you now, fine, John. Yeah, no, thanks. Yeah.
Yeah, sorry, it's just that I'm in a restaurant cafe thing on the motorway at the moment, so the background noise.
Oh, that's okay. Don't worry.
It was just I was trying to work out, because I've heard about the ground source heat pumps being sort of less intrusive, should we say, and that's why I was wondering about that. But I think you kind of answered that.
Yeah, I mean, you still need a big garden, because either you have to put a slinky coil in all the way around, or you've got to put six boreholes in. I mean, it's less intrusive in terms of it can all be buried underground, so you don't actually see it, but it does come at quite a cost. And there's a lot of debate I have with manufacturers where ground source heat pump people will say it's more efficient than outside, where typically they quote about sort of 3.5 to 4 to 1 efficiencies. But that's all year round. And I do then say, yeah, but we can get much better efficiencies on air source heat pumps in the summer with hot water. And they don't seem to want to discuss hot water use, and indeed nor do air source heat pumps, because it's a variable. It's difficult for them to quantify how much hot water you're going to use. But it can easily be half the bill. Hot water could be half the bill, and you could get tremendously better efficiencies of that hot water in the summer. So I'm not convinced that the manufacturers know all the information to give us that statement that ground source is much more efficient than air source. It's an awful lot more money to install, for sure, and if it goes wrong, it's much more expensive to put right.
Okay, so that's great then.
Does that help,
question I had was, yes, no, that's great then. The other question I was trying to type in is landlords for residential properties are going to have higher energy conservation levels from these DP reports need to be, I think it's grade C or above in 2025. Are you going to offer a service for landlords to advise how to improve their energy conservation?
I mean, yes, we do offer a service to go around to buildings. I'll be 100% honest. At the moment, we don't necessarily offer it to domestic houses, probably because our time works out being quite expensive to do all those audits. But we certainly do it on on blocks of flats where it's obviously and commercial. We do it on all the time on. Yes, I mean it's going forward. It's going to be quite a challenge on quite how we get all this and where the advice comes from.
Yeah.
You know, I don't really know quite all the answers are going to be, but it's certainly a challenge coming forward. And
I think it's also getting it from the right source, because, like you said earlier, the salespeople will always tell you better results than you get in your life, whereas someone like yourself will give a more accurate report.
yeah, I mean, I'm always worried when the salesman's trying to sell you something he makes a profit from. You know, at least I'm trying to do a design which I'm being paid for, as to whether you put A in or B in.
Yeah.
You know, it's always where, I mean, you know, I was recently involved in quite a large school, and the headmaster wanted my advice on. They had a lighting manufacturer come in, and he could save £12,000 a year on the electrics bill by putting LED lighting in with automatic controls. And I said, well, you know, there's no question that the LED lighting is more efficient and would save money, but can I have a look at your bills, and can we have a look at that, because that's quite a saving. And he pulled out his electric bills, and he spent £4,000 on electric last year. So I said to him, well, if you only spent 4,000, I don't know how you're going to save 12. And then when you drill down into the maths of the salesman, you know, he assumed the lights were on 24 hours a day, 360 days a year. Now, there ain't many schools open on Christmas Day, is there? And, you know, and then he was assuming sort of other efficiencies to make his sums add up. But so, you know, the devil's always in the detail. I did see a question come up about is hydro the answer? Possibly. I think Tom would be the answer. There's a lot of problems with it. They say there's not enough water in the world to extract the hydrogen from, and it runs at different pressures, and it has different volumetric readings, meaning that large parts of the gas network have to be changed, and elements of the boilers would be. I think it's a possibility, and there's certainly going to be some buildings that you just have no other option other than to carry on having some type of gas type fed installation. You know, where there isn't enough power or there isn't enough physical space. So maybe hydrogen is part of the answer, but the government at the moment is pretty well committed to massive wind and solar generation, and now nuclear, with obviously the troubles about Russian gas. You know, maybe hydrogen will form part of the strategy as a possibility, certainly. Any more questions? I see we've lost a few people, but hopefully that was useful. And I say Sarah has got your details, so she will send you a copy of the video. And if you get any more questions, just give me an email or give me a ring. And thank you ever so much for coming and listening.